Thank you, Chian, for the nice introduction. And I really appreciate the effort of all the organizers of this seminar series. I think this is a beautiful resource to our community. And again, thank you for having me here. And as you said, I'm going to talk about a Riemannian manifold approach to construct informed sampling methods. So here is a brief outline of my talk. I will begin with a brief description of the Metropolis-Hastings idea. And given the background of the audience here, I will keep that description pretty brief. Then I'll talk about some of the informative Metropolis-Hastings algorithm that have been available in the literature and are popular nowadays, namely the Metropolis-adjusted Langevin algorithm, in short MALA, and the Hamiltonian Monte Carlo algorithm, in short HMC. Then I will talk about the manifold variants of these algorithms that have been developed in the literature. This will lead us to the discussion and construction of a new approach to construct a geometric MCMC method that I'm going to describe here. Then I'll talk about some results on for comparing Markov chains with the same stationary distribution. These are some general results, which we will then use it to compare the proposed geometric MCMC method with some other algorithms. And finally, I'll give a bunch of examples to demonstrate the results, the performance of the proposed algorithm. So for the audience here, we don't have to convince that we often face a situation in statistics, machine learning, and many other areas where we have a target distribution, a target PDF or PMF, which I'm denoting by pi. So throughout my talk today, pi is the target PDF, okay, that you want to explore. And often this pi is known only up to normalizing constant. So for example, in Bayesian statistics, we know that the target posterior is proportional to likelihood times prior, but the normalizing constant, the marginal density, is not generally available in closed form. And we are assuming situations where direct IID sampling from pi is not feasible, okay, is not practically feasible. So in MCMC, what we do, we run a Markov chain with, just one second. With this pi as its stationary distribution. And then we run this chain for some iteration and use these realizations of this Markov chain as approximate samples from pi. Now, there are many different many different MCMC algorithms available for constructing such a Markov chain. And Metropolis-Hastings is the predominant among these algorithms, where we basically draw a proposal Y from almost an arbitrary proposal density Q, and then we accept or reject that proposed Y as my next value of the Markov chain, that is the value of the Markov chain for the next iteration, for the next step, with certain probability, okay? And as you can see that probability alpha, which I'm writing here, depends on pi only through the ratio. So the normalizing constant of pi cancels out, right? Now, as I said, Q is, quite arbitrary. So that means many choices of Q can be done. One popular choice is what is known as the random walk Metropolis algorithm, where we take the conditional density Qy given x is f of y minus x for some density f. And in particular, if f is symmetric about the origin, then you can see the acceptance ratio formula, the Q cancels out, right? So it simplifies. And a particular choice of f is a normal density. Is a normal density, which is centered at my current value x. And you can see, so this proposal density has this one parameter, the tuning parameter, which is the variance of this random walk. And the larger values of the variance will propose larger move, but at the same time, it might lead to less smaller acceptance rate. So this random walk proposal is very popular because of its simplicity, and also that a single parameter h can be used to tune the performance of the algorithm. Okay. Now, on the other hand, you can see that this Q doesn't use, this proposal doesn't use any information about the target. And this generally leads to slow convergence and bad mixing in higher dimension. People have observed that. And these led to development of other MCMC algorithms, other Metropolis-Hastings algorithms, which uses a proposal that involves some information about pi. For example, the mean of the Mala proposal, you can see that it involves the gradient of the log target. Similarly, the Hamiltonian Monte Carlo also involves the gradient of the log target. And the hope is the Markov chain, by doing that, the Markov chain is going to move towards the higher density, higher mass area of the target more quickly. And people have done various analysis, asymptotic analysis to in fact demonstrate that, as well as empirical analysis in the finite sample. On the other hand, when the target is pretty complex, for example, the target is multimodal, or the coordinates of the target are highly correlated with highly varying marginal variances, the so-called Mala and HMC algorithms are also known to suffer and the convergence and the mixing behavior. So this led us to develop what is known as the manifold variance of these algorithms. Now, the probability density functions, which is our targets, lie on a Riemannian manifold with a natural Riemannian metric, what is known as the Fisher-Rao metric, which has been shown to have very nice properties in terms of the invariance of the parameterizations, giving us the geodesic path and so on and so forth. And the idea is to use that to construct MCMC algorithm. Indeed, Mark Girolami and Ben Kilder had proposed the manifold Mala, where they basically use this natural geometry on the target to construct the M-Mala proposal. And as you can see, the the M-Mala proposal density is quite complex. It involves the higher order derivatives of the log target, and the metric changes with every iteration. It's position-specific metric. For example, you can see the variance covariance matrix is the inverse of the Fisher information matrix, and it changes in every iteration. So it leads to high computational burden because it generally involves cubic scale computation. Similarly, in that paper, Riemannian manifold version of the HMC was also developed, where they generalized the Euclidean Hamiltonian function to a generalized Hamiltonian function. And in that case, what happens is that the leapfrog integrator that we use, the numerical integrator that we use in the regular Euclidean HMC doesn't work anymore. So they had to develop a generalized version of the leapfrog integrator, which involves solving fixed point equations, and that solving that it requires high computational burden. Okay, so the point is, there are several examples have been shown that these manifold versions of those algorithms improves the performance of the Euclidean versions of this algorithm, but it involves high computational burden. And also, these are only applicable for continuous targets because it involves derivatives and stuff. Although there have been some attempts to embed a discrete target into a continuous space and then applying the HMC and Mala, not the geometric algorithm. But that generally destroy the topological structure of the discrete target, and these methods are also not applicable all the time. There are some other approach recently developed in terms of locally informed, locally balanced proposals. Again, these are not, taking into account of the geometry of the manifold structure of the target space in the discrete case. So the goal of my talk here to develop a manifold MCMC algorithm which will be universally applicable to both discrete and continuous space, and as well as computationally efficient. So as I said, the Fisher-Rao metric is a natural metric, and it has very nice properties. It has been used in other contexts, but in MCMC, using it leads to high computational burden. So I'm going to consider an approach which I think in statistics was first used by Bhattacharya in this 1943 paper, so known as the square root transformation. So if you take the square root transformation of the densities, then the transformation space is an L2 space, is simply a positive octant of the unit sphere. And being the unit sphere, I can find out the geodesic path, the exponential and the inverse exponential, the logarithmic map in closed form, which are not available. And in fact, in the square root space, the Fisher-Rao metric simply becomes the, the inner product, right? The standard L2 metric. So the idea is to construct my proposal of the image density using these square root transformation. Note that in a regular random walk, what we do, if you are currently at X, we draw a perturbation from a normal mean zero normal density, right? And then the proposed move Y is simply X plus I. So we simply do a Euclidean perturbation to my current X. Without taking into account the geometry of the target. Instead, what we are planning to do here is we'll take that uninformed random walk proposal density and we'll move it towards the target according, taking into account the geometry of the space. So F is that my uninformed baseline proposal, the random walk proposal, and I'm going to move it towards pi. So suppose I use k such directions, which I'm going to call as k such PDFs G1 to GK, along which I'm going to move these my F according to the geodesic path. Now, these densities, these GIs can be some local or global approximations of F, but it doesn't have to. You can see, we'll talk about examples. It can be quite non-informative choice too. And I'm going to do it in the square root space. So suppose I take the square root F, and remember the tangent space is linear. So I'll first take the inverse exponential map, which I'm denoting by chi, according to these directions specified by G. And then I'll take the exponential map to map it back to the square root space, and then I'll just simply square it to bring it to my the space of densities. And as you can see, by varying epsilon from 0 to 1, I'm covering the geodesic path from square root F to square root G, right? So these are what I'm calling the perturbations, the epsilon perturbations of the baseline density, but where I'm taking the geometry of the, the target into account. So naturally, the question is, is this proposal density available in closed form? Can I sample from it? So you can see that this map has a simple structure. It is cosine of again, theta is the arc length, the angle between the square root F and square root G, plus sine of epsilon theta times this this zeta I. And remember, I have to square it, right, to bring it to my space of densities. By the way, this theta is bounded between 0 and 90 degree. The angle is 0, that means the two densities are exactly same. And the maximum it can take is 90 degree. And squaring it, this is what I'm taking as my, the proposal density for the ith, for the ith direction. And you can see it has a simple mixture structure. And this is the geometric image algorithm. Okay, so I propose Y from this, mixture density, And remember, so AIs are simply giving me the probability of moving in the direction GI. Again, K can be simply 1. So in that case, it's simply phi1, which itself has a mixture structure. And then I accept or reject this Y according to the MH acceptance probability. Okay. Let me know if there is any question. So
very quickly, what is f of y given x again? I'm sorry.
So f is that, any proposal density that you would be using otherwise. Like I said, random walk proposal.
I see.
Or it can be a Mala proposal, or can be an independent proposal.
Okay.
That I'm just moving this f towards my target to construct my geometric proposal.
Okay. Thank you.
Okay. Now, in order to be, practically useful, I have to be able to sample from this proposal. And remember, this proposal has a mixture representation, and each of these mixing density also has a mixture representation. So that means in order to sample and from it or compute this, I have to be able to compute the weights and compute the and also be able to sample from F and H. Remember, F is the baseline proposal that people use generally. So that we know how to sample from it. Like, for example, the normal random walk or an independent MH proposal or a Mala proposal. So we have to be able to then, so this boils down to calculating theta, the angle, and be able to sample from H. If both F and G, these directions are both normal, then these thetas are available in closed form. The inner product and the angles, they're all available in closed form. And if they're not normal, so which is generally the case, we'll be generally using normal, right? Normal random walk and normal GIs. So this is available in closed form. If not, there are many ways things can be done. So one is we can see that these inner products are simply, can be written as an expectation with respect to G or F. So we can compute this by, say, importance sampling. And in particular, if F or GI do not depend on X, my current value X, either of them, I can just use only one sample, like one big sample to compute it. So I don't have to do this, every time, do the sampling every time. But again, if F and G are normal, which is generally we'll use, then this is available in closed form. So that means all I need is to be able to sample from H. We could show that H is bounded by a constant M, which I'm mentioned here, times a density U, which is a mixture of F and G. So that means I can use a rejection sampler to sample H by basically getting a sample from U and then accepting with certain probability. This M is bigger than or equal to 1, and obviously closer to M is closer to 1 is good. And you can see when theta is around 90 degrees, remember theta is between 0 and 90 degrees. When theta is close to 90 degrees, this M is 1. So, so I have very high acceptance rate. On the other hand, when theta is small, M can be large, but on the other hand, you see, when theta is small, the mixing coefficient of H in phi is small. So generally, I'm not going to be even required to sample from H. Okay, so we have, this is a generic rejection sampler, and we have used it in many different examples, and it works quite well. In fact, we have compared it, this generic sampler, with specific problem sampling, problem-specific rejection sampler, and this works pretty well. Okay, any question? And it works for both discrete and continuous. Okay, now let me see how I'm doing on time. So, so I'm going to use some results, and giving the audience, I will just, quickly go through it. So suppose I have a Markov transition function P and a Markov transition function Q are basically two Markov chains, both having pi as a stationary distribution. So that means we can use samples from either of these to estimate the mean of some functions at t, because we know that if these Markov chains are, say, Harris-ergodic, then the sample averages are strongly consistent. But then which one should I use? Now, there are different orderings available in the literature. The efficiency ordering says that the one with smaller asymptotic variance in CLT we should use, because that will lead to smaller standard errors. On the other hand, there are other orderings in terms of spectral gap, because largest spectral gap means is faster convergence to the target, to the stationarity. So the one with a larger gap, we should use that. And there are already available results which compares what is known as the space-Kuhn ordering, which is the off-diagonal domination. So if if P is better than Q in terms of space-Kuhn ordering, that is, the off-diagonal probabilities are higher, then that results in better efficiency, that is smaller asymptotic variance, smaller lag correlation, which is called the autocovariance ordering. What we could show that if P is better than Q at least C times in space-Kuhn ordering, then P is better than Q at least C times in terms of efficiency ordering, spectral gap ordering, and covariance ordering. Okay, this is general result. Then in the context of geometric image chain, we showed that the geometric image chain at least C times better than the base MCMC chain. Remember, F, the proposal density of the uninformed image algorithm, we could show that P, the geometry proposal, is C times better than Q. So that means it is better in terms of all these other orderings. Okay, now I will give some examples. I'll start with the simple example where my target density is standard normal. I consider an independent image proposal with N11 proposal. it is known that this image algorithm is, performs very poorly. It is not geometrically ergodic. In fact, you can see that the alpha xy, the acceptance rate is very small when y, the proposed value is larger than my current value. So it's not going to move to the right, basically. So here is some test plots. So I ran this independent image chain for 1000 iterations, starting at -5, that is my left plot. Then starting at -10, that is my second plot from the left. You can see when I start at -5, it moves to the modal region. But when I start at -10, this chain even doesn't move at all. And this is a problem with, known problem with independent image sampler, that it can have, very high rejection. It might fail to move. It's very sensitive to the starting value. Then I use this geometric proposal with the same f, that n11, but with different g's. First, I take g to be my target, pi, that n01, which is the third plot. And here I'm starting at -30, and it moves to the target in less than 2-3 iterations. In practice, I may not be able to use the target as g. So then I use quite a diffuse g, n0 900. Again, I start at, say, -50 even. It moves to target in less than 5 iterations. And we were able to show that this geometric image algorithm is uniformly ergodic, whereas the original independent image is not even geometrically ergodic. Next, I consider a multimodal target. In particular, it's a bivariate normal mixture. One mode is at 0, 0 origin, another mode is at 10, 10, different variances. It is known that random walk suffers from slow mixing. It is trapped in a local mode. So I use a normal random walk with proposal 2 times identity, and I start at the middle, 5, 5. Then I consider 3 different variants of the geometric image. That is 3 different choice of G, but with the same F, this random walk F. My first choice is when G is a set of 2 densities, G1, G2, where G1 is my, the first density in my mixture in pi target, and G2 is the second. So basically, I'm assuming here I know the locations of the 2 modes. For the second choice, I take G to be a singleton set with G to be my target pi. For the third case, I take again G to be a singleton set with a diffuse normal density. So again, normal with mean 0 variance 900, the bivariate version of it, the diagonal covariance matrix. So here are, so I ran these chains for 100,000 iterations. The first plot on the left is the random walk, is the first 1000 iterations of the trajectory. And as you can see, it is trapped in a local mode. And it fails to come out of that mode even after 100,000 iterations. Whereas all the other choices, the geometric proposals, for all these three choices of G, they are able to find both the modes, in less than 100 iterations. So here is what is going on. I wanted to, why this geometric proposal works. So the red is my target. Blue is my starting proposal of the random walk, which is a normal. I mean, again, this is the univariate version of it. I'm just, considering the first coordinate. Normal 5, 2. In the random walk, I'm making localized moves. So after few iterations, I go to say 4.35. So that's my light blue curve. Okay, so I'm making a local move. And that's why when it goes to a mode, it just can't come out of the mode. On the other hand, the geometric image proposal uses this, remember this flat, the dark green is the diffuse G, which is far away from, from the target, but making, I'm moving the density towards it, making what I'm calling a global move, is helping the chain to come out of the mode, okay, come out of the local mode. So that's why it is able to go back and forth of the two modes. Next, I consider the Bayesian logistic model. We are all familiar with the Bayesian logistic regression model. Here, I'm using a normal prior. That's my target density. So M is the number of observation. P is the number of covariates. So the link function here is the logistic logit link. I consider the PyMa Indian dataset. I know we are supposed to leave it alone. In the paper, I also considered other choices, other datasets. And I ran different algorithms, the random walk, the geometric version of the random walk, an independent algorithm, the manifold mala, the mala, and we see that. So by the way, here I'm using k equal to 1 and G be the Bernstein-von Mises approximation of pi. And that is what I use for the independent Metropolis-Hastings algorithm also. And you can see the improvement that I get in terms of effective sample size is huge from the random walk to the geometric version of it. And obviously, this improvement is less if I use, say, for example, manifold mala as my base density. But nonetheless, the geometric chain improves. And we know that the manifold mala is computationally expensive. That's why you can see the time normalized effective sample size for GMC RW is almost 3 times higher than that of manifold mala. Okay. And the independent metropolis with the Bernstein-von Mises approximation performs well. But on the other hand, if I change the proposal density of the independent metropolis, the performance suffers severely. On the other hand, the geometric variance of it even with a bad independent proposal, it's not that much affected. It's not, affected at all. And when the dimension here, P of, the target dimension is 8, when the dimension changes, these issues even are exacerbated. In fact, so the GMC RW is, for example, it can be much more efficient in terms of time normalized effective sample size than the manifold version of the mala, as as is available in the manuscript. We applied on other data sets, higher dimensional data sets. Now, I have a few minutes. I talked about a bunch of continuous targets. Now I'm going to talk about a discrete target distribution. In particular, I'm going to consider an important problem known as Bayesian variable selection problem in linear regression. So here I have responses G's, covariates X. So Z is an m-dimensional vector. X is an m by p matrix. And the goal is to know which covariates, which predictors are important. A popular approach in Bayesian variable selection is to consider this hierarchical model by introducing this binary latent vector gamma. It's a p-dimensional vector. It's a binary vector. So each component takes 1 or 0. So for example, gamma 1 is 1 if that variable is active, 0 otherwise. So in the hierarchical model, the first line is the normal linear regression model. The second line is, is a special choice of what is known as the spike and slab prior. Here I'm using a particular choice of the spike. It's a degenerate spike. So when gamma is 0, beta j is exactly equal to 0. Otherwise, it's a normal prior. And then I'm putting independent Bernoulli prior on gammas and some non-informative priors on betas and sigma square. It can be the Jeffreys prior, for example. Okay. The fact that we are using normal conjugate prior on beta and sigma square, the inverse gamma prior, conjugate prior, we can integrate them analytically out from the posterior. And the target PMF of the gamma is available in closed form after normalizing constant. Now remember, gamma is a p-dimensional vector, p-dimensional binary vector, discrete space. But the target dimension can be huge, right? It's 2 to the power p, the cardinality. So generally, MCMC algorithms are used to explore this target PMF. And these algorithms available in the literature are based generally on some, local proposals. So suppose, currently, of the Markov chains, currently I'm at 1, 2. Then it considers one of the 3 types of moves known as addition, deletion, and swap. In the addition step, which I'm denoting by gamma plus, I include one of the remaining inactive variables. In the deletion, gamma minus, I drop one of the current variables. In gamma, in the swap move, which is gamma O, I replace one of the active variables with an inactive variable. So together they construct this, they constitute this neighborhood of my current gamma. And the image algorithms that are available in the literature, the proposal is simply a mixture of these three types of moves. Okay, that's the proposal density, where these coefficients B plus, B minus, and BO, that's that can depend on current gamma and sum to 1. So we will take that as our base proposal F. So to construct the geometric image, we need G. So what we do is for G, we just simply take a local version of pi, the target pi. Remember, pi is known up to normalizing constant. So I'll take G to be pi constant on the neighborhood of gamma. So that means I have to be able to compute this for all gamma in neighborhood. And we use Cholesky update recently proposed to compute G. And I compared this performance with the image algorithms on a bunch of simulation examples. I'm showing here one where the entries of X are generated from independent normal. There are true 5 covariates, and the P is 10,000, M is 400. The number of responses and the number of variables covariates is 10,000. So it's high dimensional. And I do prediction also, so I take a same number of observations as my testing data set. And I compare two kind of random walk I use. One is which is known as the symmetric random walk, and another choice of basically, as I said, choices of this mixing coefficient B's basically changes the image algorithm. So another is again from a recent paper, I took 4.4.4.2 for these three types of moves, and here are some results. So these are based on 100 repetitions. So 100, simulated data sets. Each time the random walk chain was run for 50,000 iterations, both of these, right? 50,000 each. Whereas the geometric versions of it, the GMC, were run only for 100 iterations. Okay, and every time we start at the null model. So what we call a success is basically whether it is able to find the posterior mode. And you can see that the geometry Monte Carlo was able to find the posterior mode every time, 100% success. The symmetry random walk performed a little better than the asymmetric random walk, but still, they are not able to find almost 40% of the time the posterior mode. And among the successful runs, it took around over 30,000 iterations to find it. Whereas the geometric method was able to find it in 10 iterations or less. And the time to find, obviously, for the GMC, it took is much less. And it leads to, so then we look at the median model, which is generally used, in the Bayesian variable selection. We calculated the mean square prediction error, the mean square error in beta, and geometric methods performs much, much better. The coverage is defined in terms of whether the median model was able to capture the true model. Geometric methods did it 100% time, but not, as you can see, random walks suffer. And the Jaccard index, which is the intersection of the median model and the true model versus the union, we have 100%. Okay, because we find the true model every time, and only the true model. We also applied it on a real data set where P is close to 1 million, but for the sake of time, I'm not, let me not do that. So, this is implemented in an R package, geommc. It's very easy to implement geommc.vs function, which implements this variable selections geometric sampler. You only need to put X, Y, the covariate matrix and the observations. And, if you have a variable selection problem, I would request you to give it a try.